He talks a lot.
وعليكم السلام ورحمة الله.
Student or not?
No, he failed the courses multiple times.
And if someone is great at talking, then like what we have.
مش أكيد.
أنا أرسلت له إيميل المدير قلت له
أنا ما بعتبر شيء. don't worry. بس ما قاليش عن الموضوع.
عشان تخلي لك هو هو يمكن يدرس one course with anyone to help معه. But this is not cannot tell the show you.
Who's the second exam?
See?
Then.
Then Chandani is the next.
What is she?
I will not register. لكن I will work ونخلص الشغل بتاعي في April و present. خلص April وما شفناها ويخلص ماي ومتي جون.
I sort of forgot about it yesterday. Someone yeah, but it was not.
Yeah, I got access review rejected it. ما بتعرف شو المشكلة مرة هي زي فوق في الريفيور.
Yeah.
وفوق في الريفيور أعطاني جريدة. Don't know whether to email الأسوسييتد. يعني أنا I want to tell him but I'm hesitant. I want to tell him look if next review you plan to add a new person let me know I'm not willing to submit. بعدين قلت okay if he tells me I'm willing. هو تطلع له فقاس وقال لي yes I'm willing. What will I do? I have no other option. It's an excellent work. حرام ناخذ I work on it.
Is it easy reviews?
I think they are somehow feasible. Not easy, but time consuming.
Yeah, ونين على البيبر.
أنا وماجد وأحمد ذبح فاضل وابن شاين.
I remember.
اشتغل مع فاضل قبل.
السلام عليكم. This is my lunch. You want to share with me? تفضل. والله جاي سلام عليكم. جاي من straight from another thesis. والله I finished my lecture. Hello شرف.
السلام عليكم.
السلام عليكم. Good luck إن شاء الله. وصلنا مع أحمد عثمان ومحمد عندهم students. زين. I told them I'm late for the next one, so sorry. I was late for the first and I'm late for the second. Sharaf, good luck, inshallah.
Okay,
This is the team, right?
yes, we're the team. Do you expect anyone to join? No? Can we start?
Yeah, we can start.
Okay, so thank you everyone. Today's is Sharafa's presentation. It's a research thesis on behavioral modeling of power amplifiers using the real-valued time linear network. So Sharafa, you'll have 30 minutes.
Okay.
To give us your presentation, and then we'll ask you questions.
Okay.
Thank you.
Okay. Sorry. Hello, good afternoon. My name is Sharafa Idowu Bankole, and here I would like to present my thesis titled Behavioral Modeling of RF Power Amplifier using real value time delay neural network. This is the overview of the presentation. We have the introduction of RF amplifiers, the research objectives, the proposed neural network models, the key results and contribution. Power amplifiers, as we know, they are device that can be used to amplify signals. So these power amplifiers, they have some challenges, and the major challenges they have is the non-linearities and memory effects. And there is a need for us to model the behavior of the power amplifier. And why do we need to model the behavior of the power amplifier? Because for us to achieve this, the power amplifier as this, it's non-linear. Now, because of that, we need to create a predistortor. The predistortor is a function whose behavior is the inverse of that of the power amplifier. So that is why when we get the behavior of the power amplifier and we need to send a signal, then the predistortor will precompensate the signal to distort the signal in a tailored way such that by the time it passes through the power amplifier, we'll get a linearized output. And that is why we need to model the behavior of the power amplifier. Okay. So there are several models that have been proposed to actually deal with this issue. And our objective here is to develop an efficient neural network model for this power amplifier, and also to minimize the NMSC while maintaining low complexity, and also evaluate the models on real-world power amplifier prototypes using 5G test signals. Okay, so we have gone through the literature, and what we are able to scout from the literature are the type of models, the non-neural network-based models and the neural network-based models. And we are also proposing a neural network-based model. We are want to go through the literature here, the categories of the non-neural network-based models. So we have the lookup table model. The lookup table model also has its own categories. We have the nested lookup table, the memoryless lookup table, and the hybrid lookup table. The hybrid lookup table is actually combination of the memoryless lookup table and the nested lookup table when they are combining a mutually exclusive pattern to be able to generate and improve the version of the lookup table. Yeah, but it has several limitations because it does not capture the memory effects in the power amplifier. So because of that, the Volterra series is also another category that is found in the literature, and it also has two categories. We have the traditional Volterra series and the pruned Volterra series. The pruned Volterra series actually cuts down the number of coefficients in the formula, and from there it's able to generate behavior without excessive complexity. And also we have the low pass equivalent Volterra series and the baseband Volterra series. So those ones, the LPE uses the pruned Volterra series to actually minimize the complexity, while the baseband equivalent Volterra series does not really need to reduce the complexity. It minimizes the complexity differently, but not without pruning the formula. Okay, so we also have the memory polynomial. We have the generalized memory polynomial and memory polynomial. The only difference is that the generalized memory polynomial has cross terms. So that captures the behavior of the amplifier in a better way. So another one is the Wiener models. So we have the augmented Wiener models and the traditional Wiener model. For the Wiener models, it actually uses the FRR filter and the linear FRR filter and the non-linear static block, the one that actually contains the LUT. This model with the LUT as the second block of that Wiener filter. While the Hamilton model actually has the block first, the non-linearity block first, and the linear filter next. So there are also another category that we also found in the literature, that is twin nonlinear two-box models. So the boxes, there are two boxes, nonlinear two boxes, and the two boxes, we have the forward twin nonlinear two-box models, reverse two-box twin nonlinear two-box model, and the parallel twin nonlinear two-box models from there. Okay, so these are the ones we found in literature concerning the non-neural network-based models. Now, for the neural network-based models that we also found in the literature, we have the real value time delay neural network. So these ones, they also categorized into real value focus time delay neural network, the augmented real value time delay neural network, the phase normalized time delay neural network. So they actually one uses the phase instead of the Cartesian and the Cartesian form. Also the block oriented time delay neural network and the fully connected two hidden layer artificial neural network. So we have the ones that use convolutional neural network. So the other category that we have found in the literature, that the power temperature inclusive real value time delay neural network and the real value time delay convolutional neural network. Then we have the LSTM and the bi-LSTM. So those ones, they actually use the LSTM means the long short-term memory. So it's also another category of neural network model. And so we have the different ones. The LSTM uses two parallel LSTM to capture the behavior of the power amplifier better. So we have the JNet as well. Those ones they use recurrent neural network to actually capture the behavior of the power amplifier. So it's also as a category. The phase gated JNet and the DVR JNet, that is the decomposed vector rotation JNets. So these are the ones we also found in the literature that will actually capture the model, the behavior of the power amplifiers. Okay, now we want to talk about the neural network function. Yeah, because we're actually using the neural network model. And in the neural network, we have the inputs, the weights, and the bias. So when they get into this network, the input multiplies the weights and the bias is added. Then activation function is applied to it, and different activation functions that we have. But in this thesis, we are going to be limited to three major activation functions. One of them is the ReLU activation function. So this activation function, the output is the same as the input as long as the input is greater than 0. Yeah. Then we have the sequence activation function. It restricts the outputs between 0 and 1. So we're getting, so whenever the input is imputed into the system, then the output will be generated between 0 and 1. And we have the branch activation function, which is a steeper curve, and its own output is between -1 and +1. And this is the okay. So our proposed model. So we are proposing 3 two-box models. So we have a model A, model B, and model C. So these 3 models, they are two-box. Each of them is a two-box model. One is the real value time delay neural network for model A. We have the real value time delay neural network and also another real value time delay neural network. So the output of the first one is the input of the second one. Okay. So for model B, that one is a real value neural network, and this is augmented real value time delay neural network. And model C is augmented real value neural network. The output of that goes to augmented real value time delay neural network. And these 3, they are now compared with benchmark. We have a benchmark which we use to a one-box model. So and it's augmented real value time delay neural network. So this is our model A. So this is how it looks. So we have the inputs, inputs. The inputs, these are the inputs, but these are the interface and the quadrature components of the signals. The other ones are the delayed versions of the signals that are generated. So, and when they come into the network, the output generated, they now serve as the input for the second box to generate the outputs. Okay. So, and this is the model B. So this model, so the I and Q, based on the quadrature, they come into the network and it generates this I and Q from the output. Then this I and Q, they are now used to generate the inputs for the second box. So then for the model C, we have the I and Q as well as the magnitude, the square of the magnitude and the cube of the magnitude. So they are used to generate I and Q from for the first box. So those ones, they are now used to generate the input for the second box. So these are the three models, and this is the benchmark model. So this is the one we get everything with. Okay, so our methodology. So first is that we got our data from the laboratory, from our laboratory here. We have two set of data. We have it generated 40 megahertz signals from our laboratory here, and we also got the 100 megahertz signals from our colleague in the University of Calgary in Canada. So, because the one we have here is an extended version of the one we have here. The one in Calgary is an extended version of the one we have. So that one generates 100 megahertz signals for us. So, and we will subject them to preprocessing and normalization, and use a neural network to get our models. So from the data, we have the interface and the quadrature components of the data, and derive the magnitude, the square of the magnitude, and the cube of the magnitude from there. Also generated the delayed components from it. Okay, the hardware, the amplifier, the power amplifier that we use in this research is the gallium nitride power amplifier, and the data set, like we said earlier, 40 megahertz and 100 megahertz. So, and the metrics for the normalized mean squared error, that's NMSC, and complexity, those are the things you have to stick for. Okay, this is just a rough estimate of what happens in the neural network. So here we have the layers, the weights, and different layers, and we get the predicted outputs. Then we have the target outputs. So the loss is what generates the NMSC, and the optimizer. So there is an optimizer. We use Adam as our optimizer to actually adjust the weight of the network. And this is the test conditions. We have the number of layers, number of errors, the batch size, the epochs, and the training, the validation, and the test ratio is 60 to 80/20. Number of data sets is 155. Our optimizer is Adam. Okay, so we want to see the results of our model for 40 megahertz and for 100 megahertz signals. For 40 megahertz signals, yeah, this is how the model is structured for model A. This is model A. So this is the first box of that model, and this is the second box of the model. Yeah, the numbers we can see at the top here, these are the complexities. So the complexities. So for each of these, each of these is also having its own complexity, but they are down here. It's like back of slide. Now here, in the first box, what we're actually doing here is that we set the first box activation to red and vary the second box activation from sigmoid to tanh to red. So we now find the one that gives us the best NMSC and complexity. So that is the one we selected as the two box activation function pair for that model. So yeah, for when the first box is red, we have a regular activation function giving us an NMS of minus 41.1 and a complexity of 2464. And when sigma happens to be the first box activation function, and we vary this, so what we come up with, we are able to determine that simultaneous activation gives us a complexity of 859, while the NMS is minus 38. And when the fourth box is tangent activation function, and this is varied, then we generated the one that gives us the best performance to be the tangent value, which is 2389 complexity and minus 41.48. And when we compare these three, we see which one of these three gives us the best performance. Here, we found out that the one with lower complexity and reasonable NMSC is the sigma tangent activation function. Because here we are considering trade-off between complexity and performance. That's why we actually selected this. Okay, this is the table of summary. It's telling us the different, giving us the summary of what happens in the data structure. Okay. So this is for model B. The same is also applied to model B. So for this model B, the same thing, just as what we explained earlier. So sigma activation function gives us the one that gives us the NMSC of minus 40.7D at a complexity of 64 and 644. So, and this is the table of summary, summary of this. You can see from here is that the complexity of the sigma activation function is less than half of that of the value and the time sigmoid, with also an NMSC of 40.7. Okay, so and this is model C. So we also the same thing is also applied to model C, and we also generated a time-stance activation pair to be the optimal activation pair for that model, and the complexity is 544, while the NMS is minus 9.9. So this is the summary of the model of model C performance, and the one that gives us the best performance is the sigma activation function. So here, the benchmark model. So like we said, we are comparing everything with the benchmark. So we also need to pass it through the value sigma and touch activation function. And the one that we see that gives us the best performance out of the three is the sigma activation function, having complexity of 92 with an NMSC of minus 39.2. And this is the summary of that of the benchmark model. Now we now compare the three models with the benchmark. So when we compare the three models, what we see from here is that the model A, model B, model C, and the benchmark model. So the one that gives us the best NMSC as well as the best complexity is when we also compare trade-off. We also look at trade-off. So we look at trade-off, we also look at the complexity to see which one gives us the best out of the three. And we eventually picked model B to have be the one having the best NMSC as well as a reasonable complexity. So this is the summary, the table presented in a better way. Now our key result here is that model B is the one that gives us the optimal model, the optimal performance in terms of complexity and NMSC performance. So which is the best for 40 megahertz signals. Okay, so we want to look at the 100 megahertz signals. So as for the 100 megahertz signals, so we now have this. So the same procedure that we apply to the 40 megahertz signal, we also apply the same to the 100 megahertz signals. So what we have achieved here is that the time signal activation function gives us an NMSC of minus 7.9 dB at a complexity of 1939. So for this is the summary of the table. And for the model B of the 100 megahertz signals, got an NMSC of minus 10.9 dB and a complexity of 949. Then for the model C, got an NMSC of 834 and a complexity of minus 37.2. And this is the summary of the performance of model C. Okay, so here we look at it. We look at the benchmark model as well. We pass it through the radio segment and time transformation function, and we also got NMSC to be minus 7.9 dB at a complexity of 1927, and this is the summary of that benchmark performance. And yeah, when we now compare the three models with the benchmark, and we are able to determine here also that model B gives us a reasonable NMSC as well as a reasonable complexity. So for the 100 megahertz signal, we're also able to determine that model B gives us a complexity of 949 and a reasonable NMSC of minus 37, which is the best for 100 megahertz signals. So this is the table comparing both the 40 megahertz and the 100 megahertz signals side by side. And also, if you look at the scatter plot of these models in terms of performance and complexity, you see that model B gets because the lower the value of NMSC, the better the model, and the less the complexity. So moving down down the y-axis and also down the x-axis. So the better, the lower the better. So this one gives us, strikes a reasonable balance. Strikes a reasonable balance between complexity and NMSC. That's why model B is actually selected. While model C is also having a very low complexity compared to the other models. It also has a reasonable NMSC. So, but model B seems to have that balance between complexity and NMSC. While the benchmark model is the worst, is one that performs worst, is models. So this is for the 100 megahertz signals. For the 100 megahertz signals, you see that the benchmark is having the highest complexity, while the model B is the one that strikes a reasonable balance between complexity and NMSC. Okay, so here we have seen the trade-offs in terms of decision, taking which model gives us the best performance. So using NMSC and complexity and the optimal model, and also the impact of the activation function selection, determining the best model. Okay, so we have been able to show that we have been able to propose two box neural network architectures, and then we have also been able to see insights on how the activation function selection affects the model performance, and also the practical application of 5G amplifiers and beyond. So also, we have seen that the complexity of the model, 100 megahertz signals, and for the 100 megahertz signals, there is a need for us to actually work further on optimizing so that the complexity can still be reduced further. So the future work here is to explore adaptive neural network models and apply models on real-time DVD systems, and also extend the models for 6G application. And we have addressed the challenges in behavioral modeling here, and we have achieved accurate behavioral modeling, and it also has a very valuable contribution to the radio frequency amplifier systems. Okay, so in our conclusion, so the three models that are proposed are model A, model B, and model C, and model B offers the best trade-off between complexity and NMSC. And two of the proposed models, B and C, they have much lower complexity and compared to the benchmark model, and also the activation function selection. So this also has impacts on the performance of the model. So this thesis actually generated two publications, and the first one has been accepted, while the second one is also going to be submitted to IEEE access. Yeah. Thank you.
Thank you.
Yeah.
Thank you, Sharaf.
Yeah.
Any questions? No? Okay. So, as executed, now we start the Q&A session.
Okay.
Close the session. Okay. Thank you,
Yeah,
Sharaf.
thank
I'm
you.
always impressed by how the timing, and more than that, when I saw 57 slides and 30 minutes, I was afraid. Even though he speaks really slowly, comfortably, he's able to make it. That's impressive.
28 minutes,
Wow.
right on time.
Wow, thank you.
So now we'll open the floor for the questions.
Okay.
Sharaf from Dr. Taha and Dr. Hama.
Okay.
I'm the external guy, so I'm not in the field, but I understand it's a great work in my opinion.
Okay.
The amount of effort that you put in and the presentation is to an outsider like me was clear to really understand the story.
Thank you.
My understanding, correct me if I'm wrong, wanted to come up with a nice model for amplifiers so that if you want to design a precompensator or do something with that amplifier, you will do it right. If I don't
Exactly.
have an accurate model for my amplifier, I will do it wrong and it will have repercussion on my overall system performance. This amplifier is inside a series of
Yes.
and you are proposing a neural network based modeling of my amplifier.
Yes.
And you are comparing all the possible types of neural networks and is it one box or is it two? Should I use this activation? Should I use that activation between the first box? This is the idea. Very good. My comment is if you go to, don't have to go anywhere, I felt that the MSC being within 0.1, 0.2 dB most of the time. Sometimes it is, I think, up to 1 maybe. I don't think it makes a difference in choosing which one to follow. Most of the time, if I'm not mistaken, I noticed that between this one and the other, one is 39.9, the other one is 40.0, 40. You shouldn't base your decision on choosing this neural network or that on the NMSC because 0.1 dB is not a big deal at all.
Okay.
That's my opinion. Then it becomes all about complexity. Because in those cases, complexity should play a role. 2 box versus 1. I had one really or 2 questions. 1 box versus 2 box. Is there a real-time application where the 2 box will be more time consuming in real time than the 1 box? Is there such a thing? I'm just, you want to give it a shot? I don't know, I'm asking.
Okay,
this is me an open-ended question.
Okay, so that's if there is any time when the 2 box
takes longer time to process something or to process something than the 1 box. It is prohibitive in some real-time application. This is me asking this question.
Okay, well, from what I understand is that the 2 box model, because actually model the 2 box model, taking inspiration from the Hamilton and the Vienna model. Yeah, so we actually look at the fact that one of the boxes has a very low complexity and very low complexity, so that by the time we generate an output from that, so it now gives us something that we'll be able to work with to enter the second box. So um but the question is, if there is any time when the one box is complexity, is it complexity now?
Yeah, I'm asking this. I think I might even have
Okay.
an answer to help you. To help you.
Okay.
I think once you train your network that is modeling your
Yes.
amplifier, once you
Yes.
train it, I don't know if it matters if it is one box model or a two box model.
Okay.
I don't know if you noticed. If you noticed, otherwise let me know.
Yeah. What we have seen here is that after we did the one box model, which is the benchmark model,
Right.
and from what we have seen is that it has higher complexity compared to the two box model. So
it gives you even higher complexity.
Yeah, it gives us higher complexity.
Yeah.
So and because of that, that's why the two box model is more efficient and more acceptable.
Okay, so
to give
so
us
the
the
activation
answer.
functions that you considered,
Yeah, we see the activation function. Yes,
you had, I think, three or four,
three
three of
activation
them,
functions.
When
Yes,
you sigmoid and
and
the
the
tangent.
tangent. Yes, yes.
Are those the only ones available in the
No,
literature?
these are not the
And
ones.
what is the reason you picked those and you tried all, which is a tremendous work, right?
Yes.
All kind of combinations.
Yeah. So
What are your reasons for picking this and not the others?
yeah, the others in the literature, they actually, the ones I've seen in the literature, they are a combination of the Redu, sigmoid, and Tanch. So anytime we see anyone in literature, some are Tansig, so we see that it is a combination of either Redu and sigmoid or Redu and Tanch. We have seen in the literature. So we are actually
So
coming down to the
you made the combination of
we have seen that. So that's the one we have seen. So that's why we're also we actually working on trying to reduce the complexity. So that's why we are actually using the Relu, the sigmoid, and the Tanch.
But in the literature,
Yes.
two box structure, one has sigmoid, one has stage, or back to back.
Yeah, back to back. Yeah,
So
in
it's
the literature.
function that is
Yeah, the activation function,
two
the one we
functions.
found in literature is just for one box model, and it is back to back Tanch and sigmoid. Not composites like in the in the case of our own. It's different.
Again, I started my question here with my understanding of what your intention is. Your intention is to have good model
Yes.
for an amplifier so that I can compensate. Did you try? So now your analysis said this model, your network model with these activation with the two box is low in complexity and good in MSC.
Yes.
So it looks like this is my choice if I were to model my amplifier.
Yes.
Now, did you take that and say, all right, I'm going to put this one in a real system, and I'm going to use it to do the pre-compensation design on that basis, and see if my neural network did give me the right model or not. Did you try that or not?
We have not tried that, but that is the extension of our research. That is the potential for future work.
Because that's how you would convince me.
Yes.
Because you're saying I need a good model for my amplifier.
Yes.
If I don't have one, I cannot do the other things around it and make it.
Yes.
You are claiming I did choose the right model, which is mathematically you could prove that based on complexity, based on error, etc.
Yes.
But then probably the most important question is, take this model and put it in to design another one, the pre-compensator, I think, that you get rid of the non-linearity.
Yes.
Show me if that model gave you the correct model and ended up giving you the best compensator for the non-linear thing.
Yeah.
I think you
that's where
doesn't
we're
have to
working
be
on.
now. I think that's an excellent
That's what
thing
we're That's we are working on. We'll be working on that. Inshallah.
And with that, Sharafa, thank you so much. I am done.
Thank you.
I think to answer Dr. Tahir's first question about the complexity, it's a very important question because the one box model has more complexity than the two boxes combined. And
Can you put the table that summarizes, please?
yes, any of the tables that
Yeah,
you have.
that any.
Yeah, for example, here. So you see the benchmark has 1972 parameters. So for each parameter, basically it will need 1972 probably multiplication plus maybe 1971 or something like that addition. While the other one, model B, if it has only 950, will require much less processing. So to predict one output sample, model B will require less computations than model 1. But the problem is, maybe, when we are identifying the model, identifying model B is a two-step process. So we need maybe to assess the complexity of that whole process compared to identifying one bigger model, but only in one shot. From that point of view, I think we don't have the answer about the time consumption.
You are saying would the model be so model B has the both boxes included in the 949
Yes,
doesn't it?
together. Yes.
Together. So why would you expect it? That's the overall
No,
complexity.
but I think what the brief means like figuring out this, maybe figuring out that this model is better. Is it the time you spend figuring it out? Is it worth it or not? Then
Because to find model B, you need to find its first box and then find its second box.
all the changes.
Yes. And do the calculation. But maybe once you have the parameter, if you start knowing how many layers you want, how many neurons you want.
But usually this is always the argument with the internet. Yes, you take a lot of time to train it.
Exactly.
But then when you are done training,
that's
Once it is tuned, then the models
that's why I understand
the
that assumption.
Yes.
There might be some effort in tuning it.
Offline tuning.
Right. Excellent.
Thank you, Farah,
Oh,
for the
thank you.
nice presentation. Farah said it's very clear. I mean, your sound is a bit monotonic, so it was sometimes hard to just wake up at between 1 and 2. But overall, I think it's a nice presentation.
Okay.
I have just a few verification questions. First, now I understand what I saw. You mentioned complexity, I think, from the beginning, but I'm not sure if I missed it. You did not mention what does it mean, but now I understand. So it means how many multiplications or how many arithmetic operations you have in the network in your model. So this answer is that. Now I have a general question. So in slide number 6, very beginning. Again, this comes from a misunderstanding from my side. Yes. So when you introduced the topic, you told us there are so many behavioral non-neural network models that people have invested time and investigated, and this is again to fix the fact that you have memory issues and all. But then, after all of this work that has been done on non-neural network models, which I believe they're all theoretical, right? Mathematical.
Yes.
Yeah, that's what's correct.
They jump to neural network-based model, which is, I would say, more ad hoc, but because you need to train. So why was there a need to go from a non-neural network-based model to a neural network-based model?
Yeah, because the non-neural network-based models, most of them, they are mathematical formula. So, and what happens is as the number of coefficients increases, so they are not able to capture the linearities and memory effects of the power amplifier. So because of that, that's why we need to turn to neural network-based models, because those ones, they are able to actually, they are very adaptive because they can actually capture the intricate memory effect as well as non-linearities in power amplifier. So that's why we actually made use of it.
Another option is if you want to go back to use non-neural network, you have to go and find the new mathematical formula to capture.
That will capture it.
And then I have another question: is for the neural network-based models? Again, this comes from a lack of understanding.
Okay.
Is the model amplifier dependent, or is it amplifier like, for example, you were training your data using 40 megahertz and 100 megahertz data sets, So, but these were collected using a specific power amplifier, right?
Yes.
So, if the power amplifier changes, do you need to retrain the neural network model?
Yeah, if the power amplifier changes, okay. From what we are seeing, because we are trying to generalize using a neural network model, and that's why we actually test the model with two different amplifiers, one from here, one from Canada, to see the generalization capability of the model. So that's why we're able to come up with this. We're able to determine that it's also able to give us something reasonable. Even though the one from here is 40 megahertz signal, and the one over there is 100 megahertz signal. So able to generalize that, still able to do the work. Yeah.
So the two amplifiers are completely different.
Yes.
And you're using the data from there on the neural network. Trained using the data here.
No. We retrain the neural network every time. For each set of data, we retrain the neural network.
Okay, so you split your data into the training, the testing, etc.
Yes.
So I think the answer to our question is every amplifier will get its own mode.
Actually, for a given amplifier, with some neural network, you may not need to retrain the log, because it seems that neural network can capture something within the behavior of the amplifier that is signal independent. So they are able to predict. But not all of them, and we didn't do the study here. But we did some study about who I'm sorry, I'm just asking you what signal, not
amplifier. For example,
amplifier, yes.
If you have, let's say you have train using a 40, let's stick with 40 megahertz. Let's say you collect data here at 40 megahertz and you train using for a certain amplifier here, and you
have a copy of that amplifier.
You have the same manufacturer has the same amplifier. So if I take my neural network model from here to there without retraining, will it work or no?
Actually, another student is working on this. If you have two copies of the same amplifier, okay, and then you send the same signal to both. You train one and you try to predict the other. Usually there is loss of performance. But what another undergraduate student is doing is that he's adding a tiny adjustment to the model. So he's adding a function before the model, a small function before the model, a small, very tiny neural network, and then it is able to adjust the whole model so that now it fits. So it means you need very small retuning to get it to work, rather than identifying, I don't know, 1,000 parameters. Maybe by identifying only 50, fine-tune.
I think my worry is that because there is a lot of these PEs being built, so do we have to have a neural network specific model for each PE manufacturer?
Usually, yes.
Unless it is one family and you add a small tiny tuner before, which will reduce the content.
But even in that case, if you go to a third amplifier, then you need to retune that small part, because it depends on the bias, it depends on so many things.
Just my last question, because it wasn't in the slides, maybe it's in the write-up. What's the size of your data set?
Yeah, it's 153,593.
Okay. And so you had two data sets, one with 40 megahertz.
Yeah, one
and each one is around 100. What is it? This number is the combined
No, that's the number of data sets that is in the that is in the that is the output of the
40
of the
megabytes.
yeah.
The other one has probably minimum.
Remember, Sharaf, I learned it from you when you did you used opportunity.
Opportunity, yes, yes.
To tune the
Yes, to tune the
hyperparameters
model.
of the
Yeah, the beginning,
Yes.
if you understand.
So
Yes.
you relied and you did all this optimization of the hyperparameters of the model for all the ones you considered.
Yes, yes.
Same Optuna, another one. Same.
Yeah, the Optona we used that time. Yeah, it's still
Because
the
here I
same
see that
operation.
optimizer is Adam. It looks like this is a famous optimizer. I don't know.
Yeah, yeah.
There's-
Adam is a famous optimizer. Yes.
Is famous for calculating the weights and the biases. But the Optuna was used to figure out, for example, what's the best combination of batch size, number of epochs, neurons, and so on.
There's-
So
there are two optimizations now.
I see.
Hyperparameter optimization and optimization to calculate the weights of the.
Right. So Adam is for the weights.
yes.
Yes, it's for the
The
adjusting the weights and
hyperparameters,
bias.
the number of neurons and epochs is Optuna
this
or
one's
similar.
Optuna, yeah.
Something similar.
Yes.
Yeah. Thank you so much.
Thank you.
Learning here.
Okay, thank you, Sharafa. If you can give us a few minutes to
Okay.
decide your future.
Okay.
And that